Are you ready? So many hours today. Oof. All right, let's see what I want to tell you. So, welcome back. Thank you for coming one more time to these lectures. I changed a little the plan for the next several lectures, and the reason is that in 2 weeks there will be a very small conference, and so I wanted, and my lectures will be part of this conference, and I wanted those lectures to be independent as much as possible of everything else. So I moved some things around. I hope that in the end I will say everything that I meant to say, only in a different order. Mostly today I want to talk about this funny thing, parabolic induction. Two things, really. What is it? And the other thing is why. Why is this? If you open a book in representation theory of these reductive groups, any type of representation theory of these reductive groups, you will see everywhere parabolic induction, parabolic, parabolic, parabolic. And so we would like to understand, from our point of view, why parabolic induction is so important, this funny operation. Why is it so important? And just as a little bit of history, just to get started. So in this set of lectures, we're dealing with unitary representations on a Hilbert space. In fact, we're dealing with a space. And this subject began the way you might expect it to begin. People studied some simple examples. And so these, the case of SL2 is one of the very important examples. And it was studied by, most famously by Bargmann, but also by our friends Gelfand and Naimark, who also invented C-star algebras, by the way. And what they discovered is an interesting dichotomy. So there are some natural examples that you can build. Because the group SL2R naturally acts on some geometric spaces, and the most obvious thing that it acts on is RP1, like Mobius transformations. And when you study this action, if you want to get a unitary action, you have to do something a little bit clever. So I want to act by a group element on a function so as to get a new function. And the obvious thing to do is just to let the group element act on the argument in this way. I left some space here. The reason for leaving some space is that this obvious formula is not unitary representation. And the reason is that it doesn't matter how you attempt to put a measure on RP1, which is the circle, of course. It doesn't matter how you attempt to put a measure on RP1. It will not be an invariant measure for SL2R. So this formula, as it stands, is not going to be a unitary measure, a unitary representation. But you can fix it up very easily by putting in some Jacobian factor, if you like, some Radon-Nikodym derivative like this. And, well, you're not quite done. This is, you're on the road to doing the right thing here. Because the L2 norm involves a square, the right thing to do is to take the square root of this Radon-Nikodym derivative. And now it's a unitary representation. But once you get started on this, you see you can sort of play around a little bit. It would still be a unitary representation if you put in any complex phase like this. So this is a formula that makes sense for any S in the real line. And it defines not one representation, but a whole series of representations all at once. And so that's one very natural family of representations. If we're talking about, of course, as you know, when SL2R acts on the projective line by Möbius transformations, it's really an action of PSL2R because both the identity matrix and the minus the identity matrix give the same transformation of RP1. And if you're talking about representations of PSL2R, this quotient by the two-element central subgroup, as far as continuous series of representations go, this is basically it. But then there are some beautiful other representations. By taking the action of SL2R on the other space where it naturally acts, what should we call it? Let's call it H maybe, the upper half plane. And on the upper half plane, there are interesting geometric structures. First of all, the upper half plane is a complex manifold, or Riemann surface. And there are some interesting line bundles on this surface. So we could stick in here some E, which is some holomorphic line bundle, which is equivariant with the action of the natural action of SL2R. There turns out to be there's an integer family of those. And if you just look at the L2 sections, this is a representation which is far from irreducible. So if we're studying irreducible, say that, irreducible, then ordinary functions aren't going to make the job. But if you take the holomorphic functions, then you get a much smaller space. And it turns out to be, well, sometimes it's zero, depending on which line bundle you take. Maybe there are no L2 holomorphic sections. That can happen. But when it's not zero, it turns out that it's always an irreducible representation. So these are the natural examples, and they came from geometry. And the possible E's are parameterized by, as it happens, integers. Oops. Not real numbers. So there are discrete occurring representations parameterized in a natural way by a discrete number, and then there are continuously occurring representations. And it took a long time. So this is in the 1940s that this empirical discovery was made. They did calculations, and they found some examples of representations, and then they wanted to conceptualize it, and it took some time. The first thing that happened was that this procedure here of inventing representations was standardized. People figured out a general principle for building representations of this type, not just for SL2, but for SL3 and SL4, and SP2N and SOPQ, or whatever. All of these groups have a similar series of representations, which I'll tell you about today. So the whole thing was standardized, and then eventually, not only was the definition standardized, which was done by Mackey, but the reason that these representations are so prominent, this was worked out by Harishchandran. So I want to explain these things today. But here are some simple examples. When we finally end up building these representations using abstract symbols and so on, these are the ones we'll build in the particular case of SL2. Actually, as I said more than once, there are two continuous families for SL2. There's a small variation on this construction involving double cover of RP1. Okay. Great. What do I want to say? Oh, yeah, so I'd like to say a few bits and pieces about real reductive groups again. So we want to put, so we're focusing today on this first construction, but we'll see something like this coming up as well. We want to put this construction into some context, and for that purpose we have to think again about real reductive groups. And so for us, a real reductive group was just a matrix group. It should be closed in the usual topology and finitely many components. Once it's closed, it's a Lie group, according to the famous theorem of Chevalier, maybe? Cartan, I don't know. But we don't want to take GLNZ. To study GLNZ, that's an entirely different type of mathematics. So let's just assume there are finitely many components. And the crucial condition is closed under transpose, as we mentioned before. So you can think of lots of examples. For example, all of GLNR has all of these properties. And one thing that immediately comes to mind is to intersect G with various subgroups. And here's the orthogonal group. This is a compact subgroup of G, and it will turn out to be a maximal compact subgroup of G. But I want to focus on the rest of G, the part of G which is not compact, for a moment, because that's what's going to be somehow more responsible for this family of representations. So let me define a certain vector space of matrices. So these are just n by n. Maybe I'll not be too naive. Let's use this standard Lie algebra notation. In fact, the P will sit in the Lie algebra of G. Leave it like that. So it's just the set of all matrices X which are symmetric with the property that the exponentials lie inside of G for all T. Not so good. Okay. So it's the symmetric part of the Lie algebra of G. And what I want to focus on is a new, attach a new letter to something. So what I want to, P is not a Lie algebra if you take the bracket, the commutator of two, take the commutator of two symmetric matrices. Of course, you get an anti-symmetric matrix, so it's certainly not a Lie algebra. But I want to look at some maximal abelian subspace. Of P. Just choose one. There certainly are maximal abelian subspaces, a vector space. It's maybe not so obvious that it's a vector space, but it follows from the theory of, elementary theory of Lie groups, that P is a vector space, and let's just choose a maximal abelian subspace. Okay. It's a family of commuting, pairwise commuting, symmetric matrices. So you can simultaneously, according to general theory, diagonalize all of them. So if you like, after changing basis inside of GLNR, you can think of these as just diagonal matrices. We are, if you like, intersecting this set of of all matrices with the diagonal matrices. Roughly speaking, that's what's happening. It can happen that when you intersect P with the actual diagonal matrices, you get nothing, zero. But after a change of basis, then the intersection of P with the diagonal matrices will be, will be a maximal abelian subspace. Let's use a better letter. So we're talking about things in the world of Lie algebras here. Let's call this little a instead of big A. Sorry about that. Okay. While I'm at it, when we exponentiate this thing, we'll call that fellow big A. So this is some group of matrices inside of G, of course, and they're all positive definite. And they all commute with one another. Because when you exponentiate a symmetric matrix, you get a positive definite matrix. Okay, and we want to study this thing here a little bit. Maybe the first thing to say, let me go back to P for a moment. So the basic theorem is that this thing A, and therefore big A, is unique up to conjugacy by elements of K. So if you have two maximal abelian subspaces, well, they have to have the same dimension because they're actually conjugate, and indeed they're conjugate by something in K. Okay, so we'll worry about this in just a moment. So I want to say a few things about this because we have to go slowly today, not get so tired very quickly because there's many hours ahead of us, and so we go slowly at the beginning. But I also want to say some things about matrices, symmetric matrices, and skewer joint matrices, and so on, because it's these very elementary things that I'm going to be telling you about which are responsible for the general shape of the representation theory. At some point, when we discuss the representation theory of these groups, we ought to use the hypotheses that we're dealing with groups of matrices that are closed under the transpose operation, finitely many components. Otherwise, there will be a problem. And so let's just see how the hypotheses allow us to say some interesting things here. So I want to say a few words about this theorem. It's just a theorem, you know, it's a fairly elementary theorem, but it's worth to do it just for fun. But let me back up a little bit. I meant to say something about P. If you take G to be all matrices for a moment, K is, of course, all orthogonal matrices in that case. And every matrix in GLNR can be written as an orthogonal matrix times a positive definite matrix. And in fact, this is diffeomorphism. So that's just an exercise. You can build a map backwards by work out a formula for the map backwards involving logarithms, and so this map is diffeomorphism. Now, if you have a general group of this type, which is connected, then this is still true, and the reason it's still true is that the map, well, I'm just taking this diffeomorphism and I'm restricting it to some smaller k and some smaller p, which is a submanifold inside of the biggest possible k and the biggest possible p. So it's still going to be a diffeomorphism onto something. And what is this something? Well, it's going to be a closed submanifold of GLNR. That's the first thing you can say. In fact, a closed submanifold of G sitting inside of GLNR. But G and the image of this map are manifolds of the same dimension. And if you have two manifolds of the same dimension and one of them is a submanifold of the other, then it also has to be open. So the image is not only open, it's closed, and G is connected, so it's everything. I only mentioned that because we use the connectivity there. Now for any G, it's still a diffeomorphism. Whether or not the group is connected, as long as there are finitely many components, and this is one of the few places where that finiteness assumption is actually used. And this is a sort of a repetition of the previous argument. The whole thing is to show that the whole difficult part of the story is to show that every element of G can be written in this way for some K in the K associated to G, and for some X in the P associated to G. It's that surjectivity part of the argument which is the difficult part. We got surjectivity indirectly in the case of connected groups just by this little trick that the image, a set of all matrices, was both open and closed, so it was a component. Here you can't use that, but it's kind of fun just to figure out how this goes. So we have this story in GLNR. Now if you take G transpose times G, then G is closed under the transpose operation. So G transpose G transpose little g is in big G. So the exponential of 2x is in big G. And so if you multiply by itself many times, it's also in big G. Now, this is an infinite collection of elements in big G, and big G has only finitely many components, so two of these elements have to be in the same component. And if you multiply one by the inverse of the other, look at it this way if you like, some x of 2nx times x of 2mx inverse, which is just x of some 2kx, lies in the connected component. Identity matrix. Now we can use what we just proved in the connected case. That means that X is in P. Indeed, Tx is in P for all. So finally, if you look at this fellow K, K is just equal to G times X minus x, so this now is in G. So you start off with an arbitrary factorization, and what you find is that the constituents of the factorization both lie inside of G. That's what this argument proves. So that's kind of cute and fun. I'm not going to prove everything in this level of detail. This was just so we relax, go slowly. It's not today it's a marathon. Not a sprint. Okay. So what it means is that K sees the entire topology of the group. What the group looks like, here it is. The group looks like just K times a vector space, at least as a topological space. And this is very close to the fundamental reason why we insist on finitely many components. Inside of each component, there's an element of K. The number of components of K is equal to the number of components of G. Okay, that was kind of fun. And, oh, yeah, so let's go back to this theorem. So if we take this for granted for a moment, then we end up with this conclusion here, which is that everything in G is of the form K, something in K times something in A times something in K. Maybe I should emphasize here that this is not a unique factorization. It's certainly not a Cartesian product of groups. I'm just saying that the obvious smooth map from K times A times K into G by multiplication is surjective. You can say more, but that's what I'm saying right now. And what it means is that A is telling you the way to go off to infinity inside of the group. What the group G looks like is K, it contains K, and then it goes off to infinity. G, if it's not compact, must have some A, and this A is telling you somehow what the group is like at infinity. Modulo some compact directions, some compactness, G looks like A, just looks like a vector space. So we hope that A somehow is responsible for part of the representation theory, and that K is responsible for the rest, and that's more or less, to a 0th approximation, more or less what we want to show today. That's because G is certainly K times the exponential of P, but everything in the exponential of P is conjugate, and by some element of K to something in the exponential of A. All right, so as for the theorem, this is so, I'm going to show you this argument because you can spend weeks worrying about why this is true, or you can spend 30 seconds being shown why it's true. Oh, so first of all, a little lemma which I forgot to state. Each time you have one of these A's, you can always construct A by looking at all of the matrices in P which commute with a single element X. And if you think about it for a moment, you can just take any X with a maximum number of distinct eigenspaces, distinct eigenvalues, if you like. Inside of the vector space A, there is the zero matrix, and the centralizer of the zero matrix in P is all of P. Everything in P commutes with the zero matrix. That won't do the job. On the other hand, the zero matrix has only one eigenvalue, namely 0. If you happen to repeat that construction for a P, for an X inside of A, which has the most number of distinct eigenvalues, then it's easy to convince yourself that the only things which commute with that element also commute with each other, so they constitute an abelian subspace as required. Now, if you have two maximal abelian subspaces built as the centralizers of two elements, x1 and x2, above, so to speak, the trick is to choose a k which makes the following quantity as big as possible. Or as small as possible. I just need some extremum. And what I've done here is taken an inner product, and we'll just use the standard inner product on matrices, which is just the trace of transpose times. Everything here is symmetric, so it's just the trace of the product in this particular case. So choose K so that this, which you certainly do because K is compact, so that this quantity, for example, is as large as possible. And so that means that these two vectors should be aligned up as well as possible, or maybe oppositely aligned as well as possible. And so that it makes sense that that's what you want to do. You want these vectors to be as close to one another as possible. And then we know, by taking derivatives, or something else, y. That because the infinitesimal version of conjugation is commutator, the derivative is 0, and the derivative is this, and this must be 0 all time. If you think about it, that tells you that the inner product of y of x1, x2, 0, 1. But the bracket of x1 and x2 lies in K. If you take the commutator of two symmetric matrices, which are in the Lie algebra of G, then the commutator is in the Lie algebra of G, and now it's skew symmetric. So it exponentiates to something which is an orthogonal matrix. That's pretty cool. So x1, x2. So the centralizer of x1 contains x2, and the centralizer of x2 contains x1, and so according to the way we chose x1 and x2, a1 and a2 have to be the same. Just for fun, I thought I'd show you those little things, because as I said, it's very important to understand where we are using the hypotheses that G is one of these groups. Where is it? Here. And here we see just some basic tricks involving symmetric matrices and skew symmetric matrices, which make the argument work. We will not do this every time because, well, there's not even though there are so many hours today for lectures, still there are not enough hours to give every argument in this detail. That's just for some entertainment. Everyone is excited about the holiday next week? Excited? Holiday, great. I think I will not travel to see my family next week. Okay. Before we leave, before we move on to parabolic induction, let me just make a definition here. The dimension of A, which is now well defined because any two maximal abelian subspaces of P are conjugates, that's called the real rank. And if the real rank is 0, that means that this vector space P has only 0-dimensional abelian subspaces, but every one-dimensional subspace is abelian. Every matrix commutes with itself, after all. So there is no P. In other words, every matrix in the Lie algebra of G is skew symmetric, so the group is actually compact. This happens only if P is compact. And for today, the philosophy today is that we understand compact groups, that we know everything about compact groups. And this is a good place to start because many arguments or constructions are made, I don't know, inductively or recursively on this real rank. We want to find some mechanism to understand the representation theory of G, which maybe is a group of real rank I don't know, 12, in terms of various subgroups of G, whose real ranks are smaller than 12. And we'll agree that we understand, let's say, for the sake of argument, the representation theory of all groups of real rank 11 or less, and then try and understand how groups of real rank 12 look on the basis of that. So we'll see that coming up very soon. Ah, yes. A little bit more about I made a little observation here that every maximal abelian subspace of P is the centralizer of some particular element. And I said that a good way of choosing such an element was to choose any x for which the total number of distinct eigenvalues is as large as possible. And you can continue to try and understand A and the geometry of this threefold product, where is it, this thing here, in terms of eigenspaces. But it's a little better to work with what are called roots rather than eigenvalues. And the reason is that the concept of eigenvalue depends on how the group G is embedded inside of GLNR. And it's possible to take a perfectly respectable group G and by accident embed it into GLNR in a very bad way. It's possible to choose a bad embedding. And when you choose a bad embedding, it becomes very confusing to work with eigenvalues. But there's an intrinsic notion which is a lot cleaner and it's just the following thing. So what is a root? First of all, these are called restricted roots. Maybe I should stick in that word here. Roughly speaking, it means you look at the group as a group of matrices and you just pick out, you associate to each matrix one of its eigenvalues, but this does it in a more systematic way. First of all, we don't allow 0. It's not allowed as a root. And the second thing is that there should be some x in the Lie algebra of G. This is a set of all matrices for whose corresponding one-parameter groups lie entirely inside of G, as you know, such that this formula holds. So there are eigenvalues for the adjoint action. Forgot to put it in again. So continuing this discussion, inside of A, there are various maximal dimensional subspaces, codimension 1 subspaces, the so-called root hyperplanes. everyone draws the picture of SL3. Let me do that. And for SL3, we want to find a maximal family of symmetric matrices commuting with one another inside of this P. And, well, we can just choose, what should we call these? The diagonal matrices in this particular case, as you can almost always do. In order for such a matrix to exponentiate to something with determinant 1, of course, it has to have trace 0. And then the picture, of course, and so it's a two-dimensional space, not a three-dimensional space. I have a medical problem, which is that whenever I draw this picture, it's inevitably sort of rotated a little bit. It's not, I cannot draw this A2 picture without it being at a little angle like that. Anyway, there it is. So what I'm drawing here is a picture of A, and inside of A, there are the matrices where, for example, A1 is equal to A2, and the matrices where A2 is equal to A3, and the matrices where A3 is equal to A1. And they look like that. We could discuss this entire picture. It's obvious from the formula here that we could have discussed this in terms of, in this particular case, in terms of eigenvalues. After all, A1, A2, and A3 are the eigenvalues of the matrix A1, A2, A3. And so this root business is nothing but, you know, just some fancy word for eigenvalue. But it's a little bit easier to work for more complicated groups using roots rather than eigenvalues. Okay. Now you can study this situation carefully. And this is the sort of thing you do in a class in Lie theory. For each root hyperplane, there is some element and it's not gotten in this way, it's gotten in a different way that you learn about in Lie theory, or it's something you can check explicitly in any given example. What I'm about to say is totally trivial for SL3, and indeed it's totally trivial for any particular concrete example of a reductive group. And anyway, here's what I want to say. So the first thing I want to say is that conjugation with K sends A into itself. So in other words, K normalizes A. And the second thing tells you exactly what this is. This is just reflection across the root hyperplane. So everything in the root hyperplane is mapped identically to itself, and anything orthogonal to the root hyperplane is mapped to something opposite to itself, mapped to its negative. Okay, so this is what you learn about in a course in Lie theory. The strategy for understanding this is to check that it's correct for SL2, which it is, SL2R, and then inside of any reductive group, build little copies, or inside of the Lie algebra, build little copies of SL2R, and then you're in business. That's how it works in elementary Lie theory for compact groups. Okay. Now, any connected component of the complement of the root hyperplanes is called a chamber, and it's a fact that if you look at the normalizer inside of K, of A, this is a collection of transformations that maps A to itself. If you think about it, it must permute the root hyperplanes, and this thing now acts transitively on chambers, connected components. That's the sort of thing you prove in a Lie theory class. It's trivial to prove it in any given example, but in Lie theory, the fashion is to consider all groups at once, and then you have to develop some combinatorics of Weyl groups in order to see that this is true. Okay. Chamber is a component. A minus the union of the hyperplanes. So we can improve a little this theorem here. Closure of any chamber. If by A plus, I mean just choose a chamber and then take its closure. Then G is, can be written in this way, G times K times A plus times K. If G is connected, this is the best you can do. If G is not connected, there are going to be elements of this normalizer which fix a chamber globally, map a chamber to itself, and so you could do better. But this sort of improvement of the decomposition up there is as good as it gets in the case where G is connected. And this is why people like to study connected groups, because for connected groups, we have all of this very beautiful combinatorics that you see in a Lie theory book available to us. So once again, I'll just draw the same picture that we just had over here. Here's the chamber. So now we have a slightly better picture of what G looks like. G looks like a compact group times a set of directions for going to infinity times another compact group. Okay? And so in the case of SL3, there are, so to speak, two different ways in which you can go to infinity, or a third way, which is sort of intermediate between the two extreme ways. And that's it. Okay. These two ways are not the same. They're different ways of going to infinity. The group looks different in those two directions. This picture for S3. Of course, for SL2, you're down one dimension. There's only one way of going off to infinity, and what the space looks like is just a space with one end going off to infinity. It's very simple. And now I want to try to say what the group looks like as you march off to infinity in one of these directions. Let me just see. Yeah. So I guess the way I drew this I guess the way I set things up, the chamber was actually a subset of the Lie algebra, so we should exponentiate it to get something inside of the group. Of course, the exponential map for these particular groups is a diffeomorphism, in fact, a group isomorphism, so it's safe to identify A, big A, and little a. Anyway, suppose we fix an A in A+. So now let's define the following things. These are two subgroups of G, and they're defined in the following very attractive way. They're just the elements of G, which are the, well, we have to make a choice, expanding or maybe contracting directions for the one parameter group associated to H. So what I want is this equation here to hold. H. And while we're at it, let's define another group, which is just the centralizer. So I guess I'll write it in a way that makes it look similar. Okay, they're subgroups, closed subgroups. Let's just get an immediate understanding of what's going on. If you happen to be in a situation where H is a diagonal matrix like this, and for simplicity, let's assume this combinatorial order relation among the entries. For example, it could be -1, 0, and then 1 in the case of SL3. Well, we know what happens when we conjugate. You can easily calculate. Here it is. What happens when you conjugate by a diagonal matrix, namely the ijth entry gets multiplied by the ith entry of the fellow doing the conjugation times the inverse of the jth entry. And so whether that individual ij entry goes off to infinity as t goes to infinity, or it goes to 0 as t goes to infinity, or it does something in between, depends entirely on the relationship between the sizes of the elements ai and aj. So you can see immediately what this is. It's just all matrices, in this particular case, all matrices of this type. And while we're at it, L, in this particular case, looks like this. Had we chosen H so that maybe the first two eigenvalues first two diagonal entries were equal to one another, then it would not be possible to force this entry to go to 0, and this would have to become a 0. On the other hand, there would be many more entries in possible entries inside of L. But here's one example. Okay, so it's very, very elementary, especially for a concrete group like SLN. As soon as you've put the group into a form so that the A matrices are diagonal, then you see immediately that the N groups that we're building are just block unipotent matrices. They're block upper triangular matrices with identities down the diagonal and zeros below the diagonal. And L is just block diagonal matrices. So very straightforward. If you happen to choose an H, where is it? Here, up here. So A plus was actually the closure of a chamber, but if H is in the chamber itself, in the interior that is, not in the closure, not just in the closure. That's the situation here where I chose a generic matrix. The walls of this chamber, as I indicated somewhere back there, consist of matrices where these two eigenvalues agree, or these two eigenvalues agree. Vertex section of the wall is where all of the eigenvalues agree. But if you're in the generic situation where you're choosing a point inside, then n is as large as possible and independent of h, subject to this constraint. And L is as small as possible. And I could have said these two things more precisely. The n and the L that you get in this particular case have the property that this n contains all other possible n's, and this L is contained in all other possible L's. So these aren't just minimal, they're minimums. They're contained in all of the other, or contain all of the other corresponding L's and N's. Okay. there's one other letter that we want to use. P stands for the semi-direct product of L with N, just the set of product matrices. So these are block upper triangular matrices. When H is interior, as I'm discussing up here, we get, doesn't matter which interior point we get the same minimal parabolic. And this minimal fellow is contained in P for all. So it's not just minimal, it's minimum. It's the intersection of all parabolics. You may wonder how the battle works out. The more special H, the matrix H is, the smaller N gets, but the bigger L gets. So when you take the product, you may ask, how does it work? Well, here's how it works. The product is minimal in the most generic situation. Okay? So we're looking at, in the case of the minimal parabolic, so to speak, all upper triangular matrices. And in the case of other parabolics, so to speak, for example, exactly for SL3R, various block upper triangular matrices. It's not very complicated. So once again, roots are just eigenvalues, basically, and these parabolic subgroups are just subgroups of upper triangular block upper triangular matrices, basically. But the convention, since Harish-Chandra, is to speak in abstract terms, and that's what we're doing here. All right, so we're getting close to our goals here. Any questions? I owe you still. Kit Kat, for your very perceptive questions last time. Any other perceptive, interesting questions? No questions? See what else I'd like to say. Oh yeah, let me insert one word here. You could make these constructions. You wouldn't have to fix a chamber first. Of course, you could make this construction for any H in the whole world. It still makes sense to do these things. By focusing our attention on only part of A, and fixing an A, so first of all, fixing an A among all of its possible conjugates, and then fixing a chamber inside of A. We're building only some of the possible parabolic subgroups that we might want to consider, and these actually have a name. These are called standard parabolic subgroups. And for our purposes, it will be enough to consider these standard fellows, so to speak, of block upper triangular matrices. All right. Oh, one more thing before we... We're almost at the end of this matrix theory, but one more thing. Another one of these, it was Howard decomposition, another one of these factorization results, but it's somehow, well, a much better one for some purposes. Oh. This really, as manifolds, this really is a Cartesian product. Do it like this. The obvious multiplication map from K times A times N into G. In the particular case where you're dealing with an N which corresponds to a minimal parabolic, where N is as large as possible, this map here, this multiplication map, is a factor diffeomorphism. every matrix can be written as an orthogonal matrix times a positive diagonal matrix times a upper triangular matrix with ones down the diagonal. If you pick any parabolic at all, it's no longer possible to obtain such a nice factorization. But here's a very useful result, which is that the products of every element of the products of elements of K with elements of P exhaust all of G. There's some surjective map like this. Certainly not also injective. Oh, by the way, among the possible parabolic subgroups, maybe I should make a little remark here, by the way. Strictly speaking, according to the definitions, G is a parabolic subgroup of itself, because I could have chosen H to be the zero matrix. And had I chosen H to be the zero matrix, then N would consist only of the identity matrix, and L, on the other hand, would consist of all of G. So sometimes we want to exclude this possibility and consider only proper parabolic subgroups. And sometimes we don't. Sometimes it's rather convenient to notice that G is a parabolic subgroup of itself. Okay. If you're doing induction arguments, it's not very helpful to have G among the subgroups which of G itself. There's no possibility of simplifying from G to G, of course. But for other purposes, this is kind of interesting. Anyway, you see that when P is equal to G, obviously this map is not diffeomorphism. All right, very good. Now, I have something here. What did I want to say? Oh, yeah, just let's just so in particular, it may not be completely obvious, but it has to be the case that the dimension of G plus the dimension of A, which is the real rank, plus the dimension of N, in the minimal case, is equal to the dimension of G. And I thought I would just justify this decomposition a little bit by doing some little calculations. And for that purpose, we'll introduce the following operation, which sends any matrix in the Lie algebra of G to the minus of its transpose. The reason for putting in a minus sign is that this is now a Lie algebra automorphism. If you do it twice, the minuses cancel off, and the transpose of the transpose is the matrix you started with, so theta squared is 1. So just as a linear operator, theta has two eigenspaces, a plus 1 eigenspace and a minus 1 eigenspace. And the plus 1 eigenspace, because of the way we normalize things, plus 1 eigenspace is the Lie algebra of K, and the minus 1 eigenspace is P, what we were calling P before. So this packages the whole thing together. Suppose you start off with something in N. Then, on the one hand, we could average. Maybe we'll put in a half to make it proper average. Average using this involution. And when you do that, you get something which is fixed by the involution, so it lies in K. On the other hand, you can anti-symmetrize. Correct to write that thing there, and now, of course, this lies. So this shows how to take elements of N and decompose them into parts coming from K and parts coming from P. And it's this combinatorics, this very simple linear algebra, which is responsible for this identity among dimensions. I'll let you think about that. Okay. But I want to study rather than worry about this formula, just to study a generalization. This gets close to the heart of the matter. Suppose I have an H like we had on that board over there, and it's parabolic subgroup like we had over there. Let's just do a little linear algebra here. I want to take the part of the Lie algebra of L, which is contained in K. So this is the Lie algebra of the maximal compact subgroup of K, of L, excuse me. And let me add to it N, the Lie algebra of N. When I add the two bits together, what I get is effectively a copy of the Lie algebra of K, like this. This is just a vector space isomorphism, what I'm about to write down, not a Lie algebra isomorphism. So what will we do? Well, you just take any z here and you just average it, like we were doing a moment ago. It doesn't matter what you let's change one of these letters to something else, x over here, I guess. Doesn't matter what you start with, anything in the Lie algebra of G, of course, this becomes something in the Lie algebra of K. But in the particular case where you have this subspace of the Lie algebra of G, this actually becomes an isomorphism. It's easy to check. And it's a crucial fact, kind of a strange fact. I mean, this is not a Lie algebra isomorphism, but it's also not far from one. And I want to try and explain that. And for that purpose, let me think about the right way of what I want to say. Oh, yeah, maybe as a warm-up, let me explain how to go backwards from skew symmetric matrices to these block upper triangular matrices. So we'll come back to this in a moment. Here's the inverse map. So what I will do is start off with any y and look at its what I'll call a zero component and its minus component. What I'm imagining doing here is taking the Lie algebra of K, or for that matter the Lie algebra of G, and just decomposing it according to the action of Lie bracket by this matrix H here. So I can look at the sum of the negative eigenspaces plus the zero eigenspace plus the sum of the positive eigenspaces. And what I'm doing is just removing anything which lies in a positive eigenspace. sort of punchline. So what I want to do is try to explain what this means, this sentence in the box, what it means. Okay, and for that, I find it helpful to well, maybe we'll deal with groups and the algebras at the same time. Let me define a new subgroup, KT. Well, in a very simple way, I'm just going to conjugate by, which way around did I do it before? It's a subgroup, it's a compact subgroup, it's just a conjugate of the standard compact subgroup K. But now I want to add something at infinity. And for there, I'm going to just take the following thing. I'm just going to take K intersected with L. These are all compact groups. This is not a compact group, but the notation is supposed to suggest that as t goes to infinity, these compact groups converge to this group here. So these are all vector subspace, in fact, Lie subalgebras of G, and they all have the same dimension. According to this calculation over here. Now when you have a collection of subspaces, there's a sequence or a family of subspaces, all of the same dimension, it's perfectly respectable to say that the family has a limit as t goes to infinity, because each subspace just defines a point in some Grassmannian, and so you can ask, inside of that Grassmannian, do you have convergence? And that's exactly what happens. Put a little plus here. To do the same thing at minus infinity, and n would get replaced by its opposite, the transpose. Okay. So in the appropriate Grassmannian, for example. You can sort of see what's going on by looking at this isomorphism. So if I have a matrix in the Lie algebra of K, then if I conjugate it by minus th, I'll get something in the Lie algebra of D. And if I write x has a part which lies in the direct sum of the negative eigenspaces of this conjugation operation, plus a part which lies in the zero eigenspaces, plus a part which lies in the positive eigenspaces like this. And when I look at what happens in the minus eigenspace, I hope I have the signs correct. Over here, positive, yes. This goes to 0. So in the limit, so to speak, you get something which is in the Lie algebra of K infinity. Maybe this is all a little too abstract. Let's just look at SL2. See exactly what's going on here. So, of course, K is the set of all matrices which are rotation matrices. For H, we could take our friend this matrix here, and then when we exponentiate it, what we'll get is exp of t minus t, I guess. And when I conjugate, this. Talking about that. What happens if we get everything works out correctly? I get such a matrix. This. So as t goes to infinity, this term just goes away. This term just goes away, and then the rest is upper triangular. Of course, this term is blowing up, so you have to think a little bit about what's going on. But that's basically the calculation. So we defined a bunch of non-compact subgroups of G, the parabolic subgroups of G. And inside of each parabolic subgroup, there is this Ln. There is this subgroup which looks like L intersected with K times N. Here we go. And this is almost a compact group. It's not a compact group, but it's a limit of compact group. So it behaves very like a compact group for certain purposes. Enough like a compact group for certain purposes that we can make some interesting reductions from using what we know about compact groups. Okay. Any questions? Sort of entering a little bit of a lull here, just doing some experiments. Maybe it's time now to say something a little more precise. I was trying to I worried a lot last night, and then I worried a lot this morning exactly how to explain these things, and I did not come to a good decision. So let's, but let me now make a precise theorem or two. The summary so far is we defined a bunch of interesting subgroups, and we discovered an interesting feature of these interesting subgroups, which is that to a certain extent, they're approximately compact. They're limits of compact groups. And they're related to the way G looks at infinity on the one hand, and secondly, they behave a little bit like compact groups on the other hand. And we have these strange phenomena at play, and now we want to do something with these phenomena. Maybe the right thing for me is to explain what the theorem is. First of all, a little lemma, which is not a difficult lemma. It's You can think of this lemma either in abstract terms as related to the concept of amenability, or you can think of it as a baby version of the theorem that will follow. Oh, I need a little discussion, I'm sorry. I want to talk about L2 of G mod n, so I should talk about measures on G mod n. So fix a parabolic subgroup, fix an H, and then fix an N, as we were discussing before, and form this homogeneous space. Of course, G acts on this homogeneous space on the left. It's a homogeneous space. There's an obvious transitive action of G. There's also an action of L on the right, because L normalizes N. You conjugate any element of N by an element of L, then you get another element of N. So there's a right action of L and a left action of G. As for the left action of G, there is a G invariant measure. We saw this a little bit in the case of SL2R. We looked at some example last time in the particular case where N is this fellow. We saw that G modulo N was the same thing as the plane, take away 0. And the action of G was just the usual matrix multiplication action. And that preserves the standard volume on L2, or the standard volume on the plane take away the origin, because all of the matrix in G have determinant 1. So this is consistent with what we've already said. That's the good news. The bad news is that this measure is not invariant under the right action of the subgroup L of block diagonal matrices. Remember, in the particular case of this example, the right action of L just corresponded to scalar multiplication, and scalar multiplication doesn't preserve measure, of course. But the situation is not too bad. See if we can this way. Here's a formula. Suppose I have a function on G mod n, and I have an element of L. Let me define a right action of F of L on F according to this formula. X is now a point in G mod n. I'll just define this to be F of X L. In fact, I want it to be a right action, so that's to put an L inverse here. And now I'm just going to add in a little extra factor, and the correct factor is this. And now I have to just tell you what delta is. So delta is some Radon-Nikodym derivative just a homomorphism on this group L, the positive reals. I'll tell you what it is in just a moment. But first of all, the property is that this defines a right unitary action. Of L on this homogeneous space. I'm not sure we'll actually need the precise formula, but here's what it is. It's just the determinant, or the absolute value of the determinant of the map of conjugation by L from the Lie algebra band itself. Okay, now back to the lemma that I was about to state. Now that we got the measures sorted out. In this entire story, this is a story in which the case of SL2 is extremely representative of what happens in general. So the way to understand these things is to think about SL2 first. Okay, now the little lemma, which is the baby version of the theorem that will follow. The lemma says that the action of G on this Hilbert space. This is, you should think of this Hilbert space as in the first case, a simplified version of L2 of G. It's simplified because G modulo n has fewer dimensions than G. It's also simplified in the sense that whereas on L2 of G, there are two commuting actions of G, on L2 of G mod n, there's a left action of G, but a right action of the much simpler group L. So it's much easier to understand L2 of G mod n than it is to understand L2 of G itself, because you can use anything you know about L to tell you something about L2 of G mod n, whereas for L2 of G, all you can use is something about G to tell you something about G. That's not very helpful. But in the case of this space here, because there's a right action of an easy group, L, and a left action of G, you can attempt to use something about L to tell you something about G, and that's the philosophy behind this. Anyway, the first little point is that this extends to an action, a representation of this reduced C-star algebra of G. There's a correspondence between unitary representations of groups and representations of the so-called full C-star algebra, but there's a little bit of analysis involved in seeing that you actually get a representation of this so-called reduced C-star algebra, that this representation is, in the language we were using, a tempered representation. It's no big deal, but there's just a little thing to check here. If you're a C-star algebraist, you know that this sort of thing is always true whenever you divide by an amenable group. So this is certainly okay. N is a nilpotent group. But we'll look at this in a different way in a moment, because what I want to do is get to the big theorem here. Please state the big theorem. And this theorem requires one adjustment if G is not connected, quite a complicated adjustment, and it requires a minor adjustment if G does not have a compact center. So let's just assume for simplicity that G is connected and has compact center. Like SL2R, for example. SL2R is a perfect example for this theorem. I want to build an ideal inside of the C-star algebra of G, which will be an intersection of other ideals, and there'll be one such ideal for each standard parabolic of the sort we were talking about. So I want to look at all possible types, if you like, of block upper triangular matrices, where the block sizes can change. 2, 2, 1, 1, 2, 1, 1, 2, 2, whatever. 3, 1. Different types of block upper triangular matrices. And for each one, there's a representation of the C-star algebra. And that representation is the C-star algebra homomorphism, so it has a kernel. First of all, I'm going to call that representation lambda for left regular G mod n. I haven't finished the statement yet. I ran out of room. There's a C-star algebra homomorphism. Its kernel, of course, is an ideal, and the intersection of ideals is an ideal. This thing here is some ideal inside of the reduced C-star algebra of G. Let's continue the statement. I want to say that anything in this ideal is basically a compact operator, or to be more precise, it acts as compact operators on any Hilbert space of this type. I want to take L2 of G. But I want to cut down G on the right in a different way. Here I cut it down by n. Instead, I'm going to cut it down by k. And the way I'm going to do that is I'm just going to, I don't want to just divide by k. It's a little better to do the following thing. I'll take any finite dimensional representation of k, and then look at the k-fixed part of this fellow here. So now what's going on is that sigma is a finite dimensional representation, unitary representation of K. And as to this action here, K acts on L2 of G on the right. If this representation was the trivial representation of K, this would be a fancy way of saying L2 of G mod K. This would just be L2 of G mod K. What this space is the L2 sections of some vector bundle over G mod K. That's what it is in general. So this is just a slightly fancier version of L2 functions on G mod K. And here's L2 of G mod N. That's it. That's now the statement of the theorem. So let me try to explain something about the philosophy behind the theorem. Eventually, I'd like to explain something about why it's true, maybe in the afternoon. I got confused thinking about this last night, so I don't have the optimal way of explaining this proof. But anyway, let's get back to the statement. What does this theorem say? It's trying to tell you something about the spectrum, the dual of this C-star algebra. And it's saying something very interesting. It achieves what people discovered about, for example, SL2R at the very beginning of this subject. It achieves this breaking up of the representation theory into a continuous part and a discrete part, exactly as I was describing it to you at the very beginning of the lecture. So first of all, we use this terminology here. The representations, the irreducible representations of the reduced C-star algebra correspond to certain irreducible representations of G. Not all of them, but certain of them. This is irreducible representations up to equivalence. Now the thing on the right-hand side is not just a set, it's a topological space. And the closed sets inside of this topological space, this is for any C-star algebra, correspond to ideals. Closed two-sided ideals in the C-star algebra. Say, I don't know, I. If you have an ideal, you can build a closed set of, by definition, a closed set of representations, and it's just the set of equivalence classes of representations with the property that pi vanishes on J. On the other hand, if you have a collection of irreducible representations, you can build an ideal, and it's just the intersection of the kernels of the pi's of pi F. So this is the usual correspondence between geometric sets on the one hand and ideals on the other hand.